What's up, everybody? What's up? What's up? Nah, just kidding. Okay, so welcome back to this OpenFOAM video. Yep. Yes, our pisoFoam simulation has worked, and it's took I think almost half a day. It's easily like what 10 hours of simulation. Okay, so it's a kind of a thing you gotta run overnight because of the ridiculous number of time steps. So, okay, but at least you know the current number didn't blow up. It looks like it has reached some kind of steady state, and you actually didn't need that long, like 10 hours. Of course, if you want simple steady state simulation, you can use the simple foam solver. A pisoFoam is like icofoam, but for incompressible turbulent flow and laminar flow as well, depending how you use it. So these are the data files that have come out, and they look pretty good. So I'm just gonna do git add. Okay, then while it's adding, I shall just carry on elaborating on where the paraview is. Okay, so this is the usual slice filter. You can see the flow developing nicely, and it like goes fully developed kind of halfway through the thing. You have a more uniform profile. Okay, right, you have a more uniform profile towards the beginning. Right, towards the beginning you have a very uniform profile. Some boundary layer starts to develop, and where's the zoom out button? Reset, yes. And it starts to get more and more fully developed. Yep, and the bulk of the velocity is trapped in the center. And even at fully developed flow, I mean 0.1 was our inlet velocity. Even at fully developed flow, it doesn't quite go to twice the velocity as we would expect in laminar flow, and that's completely alright because it's kind of spread out, you see. So this is the inlet where it's kind of uniform, and this is outlet where the highest velocities are trapped in the center. In the color scheme, it looks a bit like you know, the laminar flow simulation, but it's if you rescale it properly. Let's see, custom scaling. Okay, so we want a 0.2 because 0.2 is 2 times of the superficial velocity. So we'll see this profile, and this is more, you know, more representative of a turbulent flow. Oops, that's very small. Okay, so I want you to notice some things. I will use the blocky version of you, and oopsie. Yeah. Well, I want you to notice that the meshing of the thing is pretty important, because you see there are lots of blue patches over here which indicate low speed, and this white patches will indicate somewhat of a slightly higher speed. So blue is like 0.05 for example, and here it represents like 0.085, something like that. And all of that, you know, the mesh has a very important part to play. You see this very streaky lines over here. And this is because our mesh wasn't, you know, really done properly. We could have done it better by adding some layers and making the mesh maybe non-orthogonal, or yeah, not this blocky shape. But I mean, for the intents and purposes of learning, this is a pretty good simulation of what pisoFoam can do. I can show you a turbulent flow through a pipe. So no problem there. Now, of course, yeah, remember, just want to recap. Okay, let me do a commit first. Yeah, just turbulent pipe flow successful. Maybe it's a coarse mesh. You just call it a coarse, not so good mesh. Okay, I'm gonna close it, and after that I'm gonna push it up to GitHub So you guys can access this latest version as well as the previous versions as well. Remember to do a git shallow clone if you are having trouble downloading this thing. Of course, yes. So, where was I? Yes. Yeah, we need to do something about the mesh and remember our boundary conditions. Yeah, once we set on the right boundary conditions, yeah, so it's deleting and all that. So git push origin master. Alright, so yeah, I can open a new terminal. Do a para view at the side. Yeah, so while that thing is uploading, just want us to know, yeah, setting the right boundary conditions for K and for epsilon is absolutely important. Yeah, so remember in the inlet, we will have some kind of okay. I think I shall use a full screen, so it's easier. Yeah, full screen, and let's see. How do I have a? Yeah. All right. So yeah, yeah. Anyway, so yeah, in the inlet we should have a turbulent kinetic energy boundary condition fixed by, you know, we learned about that last video. So GitHub software and thin pipeflow, and I'll do a double tab to show everything, and I'll do a 0.original, and that's where we put our K files. And remember how we started. We have a bottom patch of a turbulent kinetic energy inlet, and we also demonstrated, you know, how we arrive at this number, which is the inlet turbulent KE. So no problem there. So I mean, of course, we can refine this thing a bit more. We can refine this mesh a bit more so that it doesn't show those streaky lines, and it's more representative of a correct turbulent flow. But yeah, yeah, we can do that in some other video. But for now, I think yeah, it kind of shows that, you know, pisoFoam has this functionality. It's run successfully, and we run it for 1,000 time steps in the background. We're pushing it onto GitHub. It's a relatively crude but successful learning case. So thank you for watching more about pisoFoam. So that's what I have for now in the pisoFoam lecture. Yeah, so not lecture. Yeah, pisoFoam video. So yeah, if any questions, you like this, or you want to subscribe, please leave a like, comment, or subscription in the comments below. And yeah, I'll see you guys next time. Depends on what I want to do next, what I want to discuss next. Oh right, yes, of course, ideally we will have a comparison between icofoam. Yeah, icofoam, we have a comparison between icofoam, pisoFoam in the laminar mode, pisoFoam in the turbulent mode with this mesh, and then pisoFoam with a better meshing kind of a thing. Of course, we can adopt a different mesh for icofoam as well. That's totally alright, and I think it's a pretty logical thing to do. But yeah, you can check out the velocity profile and do some post-processing, which is very important for CFD. Post-processing means I want to get a velocity profile graph out, get pressure profile graph out, turbulent KE graph out, etc, etc. So yeah, that's all I have. Maybe you can do that next time, and then we can study some heat transfer in future videos as well if I have the time to do them, which I will, yeah. Well, thank you for watching. I'll see you again.